Now we're on to the last two concepts in the gases unit. We're going to talk about kinetic molecular theory first. Now, some of you may have been like me, and I looked at these gas laws and I said, wow, these guys must have been brilliant to be able to look at gases, see that they have weird properties, and test them and find these very cool relationships. And it turns out later, when I learned more about gas laws, that they actually all stem from this theory right here, kinetic molecular theory of gases. So let's talk about the 5 parts of the kinetic molecular theory. And these 5 things govern all properties of gases, regardless of what law we're talking about. So first thing is, gases are in constant random motion. This fact right here is what really separates gases from liquids and solids, the fact that they are in constant and random motion. Now, believe it or not, even though we don't see it, liquids and solids are also in constant motion. Solids obviously are in the least amount of motion, and liquids are in a medium amount of motion. And the only reason I know that these things are true is liquids flow. So I know that the molecules have to be able to move around, and gases can transfer energy. If the molecules were stiff and could not transfer energy, nothing would ever feel hot and nothing would ever feel cold, except if it was a liquid or a gas. So that's a real key point with this. But gases have the temperature has the biggest effect on gases because of this constant random motion. They can constantly transfer and take in energy and give it off to someplace else. Number 2, space between atoms is considered negligible. Think of a gas like marbles. If I were to put a bunch of marbles in a container, no matter how hard I pack them together, there will always be these tiny little spaces that are between the molecules. Okay? So you can't fit those little spheres of marbles any tighter. I'm like, you get them in packed as tight as you possibly can, but that's it. There's always going to be some gaps. So what we do is we assume that those gaps are gone. So think of it more like ooze, where if I put blobs in there, those blobs just mush together and absorb all of that excess space so that we don't have to worry about it anymore. Number 3, the energy for a sample of gas is considered constant. Okay, think about it like this. Gases are going to gain and lose energy depending on where they are. So, my classroom. When that heat kicks on, if you're directly below the vent, it's hot, and it gets really hot real fast. If you move to other portions of the room, those portions of the room might be a little bit cooler. But what we look at is, if we talk about the air in the room as being our sample, we assume that the energy across the room is exactly constant, so that no matter where you are in the room, all the molecules of gas have the exact same amount of energy. Number 4, attractive and repulsive forces are negligible. Now, believe it or not, gases do have a little bit of a positive and negative charge. So, they might be slightly positive on one end and slightly negative on the other. Well, if 2 gases are approaching each other and their slightly positive ends are near each other, they're going to push each other away at the very last second. Okay? Think of it more like a Wile E. Coyote cartoon where he's speeding down the road and all of a sudden the brick wall appears and he's like trying to skid and he slows him down ever so slightly, but he's backpedaling, and wham, he still hits the wall, but he doesn't hit with quite the amount of force that he would have if he had been going full speed. So we consider that repulsive force to be negligible. The same thing if the opposite occurs. If I get a positive and negative end close to each other, then they're going to attract and they're going to speed up as they go closer, but we're going to ignore that and assume that they are not there anymore. And the last one is, the kinetic energy of the molecules is proportional to the temperature. So in other words, the hotter it is, the faster these molecules are going to move. Remember that kinetic energy is the energy of movement. Okay? So the more energy, the higher the temperature, the faster these molecules are going to go, because they're going to have more kinetic energy as they're doing it. Okay? So just remember that if you're comparing 2 gases, the gas at the higher temperature will always be moving around more. And if the temperature is higher, we also know that the pressure is going to go up too. Okay? Ignore volume for right now. But, so if you got a sample of gas in a rigid container, if you raise the temperature, not only are the molecules going to move around more, but as they're moving, they're going to slam into each other more, which means that the pressure of the sample is going to go up. Now, these are the 5 things that are related to kinetic molecular theory. If a gas behaves according to all 5 things, then it will be ideal. Okay? So if all 5 of these things are true, then the gas is going to be considered an ideal gas. So if the gas is a constant random motion, yes. Space between molecules is negligible, energy of the sample is constant, temperature relates to the kinetic energy, and attractive repulsive forces are negligible, then you know that this is going to be a perfectly ideal gas. Now, of course, you're going, okay, Mr. Siegel, that's great, but what about a situation where it's not the case? Like your room, where it's hot in one spot and cold in another. That's not ideal. So what do we do if it's not ideal? Well, if it's not ideal, you have now what are called real gases. See? Perfect transition. A real gas, like I said, the kinetic molecular theory is for ideal gases only. It does not apply to real-world situations. Yes, all gases are in constant random motion, but it's usually the other ones that are affected if it's going to be a real gas. So what's a real gas? A real gas is the exact opposite of an ideal gas. An ideal gas was something that behaved according to the ideal gas law, and a real gas is something that does not behave perfectly under all conditions. Okay? Like I said, real world situations where, you know, the molecules are hot in one spot and cold in another, that is going to make it act more like a real gas than a perfect ideal gas. Now, under real gases, there are 2 key factors. Number 1, you must account for the little spaces that exist between the molecules. Remember, I told you before that we ignored them, but if we're talking about gases, real gases, we have to take them into account in the volume, which means we're going to subtract those spaces from the overall volume. And the other thing is we must account for the attractive and repulsive forces. So if we take these 2 things into account, we end up with this situation here. And this is a general guideline. Don't use this. This is not like a set in stone rule. This is like Mr. Siegel's shortcut to remembering how something is going to behave ideally or real. Okay, but my rule is the bigger the gas and the closer it is to being a liquid, the less ideal it's going to be. Now, what do I mean by closer to being a liquid? Think about this for a second. Under what conditions can you turn a gas into a liquid? Okay, pause for a second and brainstorm. There are 2 conditions. Try and think of at least one of them. Okay, so hopefully you've paused it. You've thought of them. Now, if you think about it, when does a gas turn into a liquid? And you're like, well, that one's obvious, Mr. Siegel. When it's cold. Yes, that's exactly right. You know, why does water droplets adhere to the outside of your glass in the summertime when you're drinking that nice cold glass of lemonade out by the pool? Okay, well, because the glass is cold, the moisture around the glass on the outside in the air hits that cold temperature and it condenses into a liquid. So you're going to have a situation where, where you are less ideal at low temperatures. Okay, that's the easy way to turn it into a liquid. And then the other one, now this one's a little bit harder. You have to remember that gases don't like attractive and repulsive forces. The only way you can have an attractive and repulsive force is if the molecules are really, 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 really close to each other. Okay, so what do you have to do to get molecules really close to each other? Well, you have to compact them. And you can't just shrink the volume on gases, unfortunately, because there's a finite size that you can get down to simply by glassware or, you know, things like that. You can't get it perfect. But if you pressurize the molecules, you can push them into a smaller area, and you don't actually have to change the volume all that much. So, under the conditions of low temperatures and high pressures, you will get less ideal gases. Could they still be ideal? Yes. But will they be less ideal? Yes. Okay. They will not behave perfectly under these situations. So low temperatures and high pressures. Okay. Those 2 things together will give you a less ideal gas. So, for example, and also obviously the bigger the molecule is too will affect it too. So, like I have here, CO2 is less ideal than oxygen because CO2 weighs 44, oxygen weighs 32. It is a physically larger molecule and is by mass it's a larger molecule, and so those things are going to play into it too. Because remember, big molecules move slower because of temperature. So if they're moving slower, it makes it easier to drop the temperature, and it makes it easier for them to be under high pressure and compact them into being having those attractive and repulsive forces. Now, let's talk about the last thing on here, is van der Waals equation. You do not need to memorize. In fact, I'm not going to even give you a calculation involving this. I put it out there because you need to see the equation and know what it looks like. Now notice, okay, in this equation, it looks very much like the ideal gas law. You have pressure, you have V, you have nRT, okay? But now you have these factors here as well. Now, the A and the B are constants. They're unique to every gas. You have to look them up. That you cannot memorize them. Every gas has their own. They're in a chart in a book, or if you ever need them, I'll give them to you. Okay? N is still moles. V is still volume. So those don't change. So you've got P plus N squared times a constant over V squared times V minus NB. So notice that pressures for real gases are going to be higher because you're adding, okay, and volumes are lower. This accounts for those spaces. This accounts for the attractive and repulsive forces. Okay, so those attractive and repulsive forces, you can see, are actually going to pull the gases in so that they collide with a greater amount of force, and then this piece, this NB, will subtract out the spaces that exist between the molecules, because again, remember, molecules are not tightly compacted together. Gases are in constant random motion, so there's actually large gaps between them because they're always moving around at all times. So these are the conditions. So again, remember, for real gases, if it's heavy, okay, if it's at low temperatures, if it's at high pressures, these three things are going to give you more real conditions. Actually, I like the phrase less ideal better. Okay? And those are the last two things in the gas laws unit. Real gases and the kinetic molecular theory, both of which basically govern everything we have done up until this point.